Alright, so hopefully you've already watched the previous video on Taylor series, and remember that Taylor series gave us an understanding of where truncation error can arise. So in this video we're going to talk about error propagation, which is another application of Taylor series that helps us see how error in our measurements lead to error in our predictions. As a simple example that I think you're probably well familiar with, these cones of uncertainty are really powerful in example of air propagation in hurricane tracking or tropical storms, because they predict not just where the center prediction is likely to be, but they also show what they sometimes call a cone of uncertainty, or a large region that may be predicted to be more likely to have the hurricane hit it. And so it's really important that our measurements or our predictions provide not just a center value, but if they can have measurements of the uncertainty, that can be much more useful in applications of that data from various end users. So the learning goals for this section are to understand how Taylor series can be applied to look at how measurement error propagates through mathematical functions and procedures. So there are a variety of different ways in which error crops up in biomedical measurements that you're likely familiar with. If you just measure your height or weight, we're familiar with that there are certain uncertainties in those measurements that could be either due to the measurement error, such as the scale might not be calibrated right, or it could be error in terms of changing from time to time, depending on what time of day you made those measurements. Other types of measurements that contain error would be measuring your temperature to see if you have a fever, or your heart rate, or your blood pressure or respiratory rate. Every single measurement that we might take from our bodies has error and uncertainty associated with that. And normally when we calculate through an equation, we neglect that uncertainty or that error. But today we're going to be looking at how we can incorporate the error or uncertainty into our predictions, which can be quite powerful. So we're asking ourselves, how does error in the measured parameters, such as the range of stroke volume, how does that affect the error in downstream calculations that might be used to evaluate patients? So there are, before we get into how you do that with Taylor series, we need to go over a couple of basic definitions about error. The first is this concept of true error, and so that's when you know the true value. And so for that, we use a capital E and then subscript T, and that's defined by the true value minus the approximation. Sometimes we're interested in more of a relative amount of error, and so instead we'll use true percent relative error. And so that's given by true minus approximate divided by the true times 100%. And so to give you a real quick example of using this, say you're asked to find the percent relative error in both the length and the diameter of this tissue engineered vessel, which is really interesting. This company Cytograph is actually doing cell-seeded tissue engineered vessels that they get implanted into various different types of surgeries. So say the length is 50 centimeters, diameter is much smaller than that, of course, and there's a certain error in those measurements. And so if you've got a half millimeter error in the measurement, in terms of how that impacts the length, then half a millimeter divided by 50 centimeters, that's only 0.1%. So you'd expect that would have minimal effect. However, that same amount of error divided by the diameter of the vessel would be a 20% error. And so that's why that could be much more serious. And so that's just an example of when it's more important to look at the percent relative error than just the true error. But it depends on the situation which ones you should be going with. I definitely look out when we have problems about which specific type of error you're asked. So that's true error. The next type of error is approximate error. And so that's when you don't know the true value, you can use an iterative approach to approximate the error. So a lot of the algorithms we'll be discussing in this course, you have a current approximation and then you update it a number of times. And so an approximate error is the current approximation, which is your best guess, minus your previous approximation, which is your used to be your best guess. You can also have percent relative error of versions of this, so current minus previous divided by current times 100%. And so the hope here, when you use approximate error, is that over time the error should be getting smaller and smaller so that to look at your converging. You don't know what the true answer is, but you're hoping that if it's converging, that means it's converging on the correct answer. So we just talked about 4 different types of error. We had true error is when you knew the answer, and that could be just the true error itself, or it could be percent relative error. And if you don't know the actual answer, sometimes we use the approximate error, which this is the approximate error, or this is the relative version of it. So this little table should hopefully simplify your understanding of these terms. They'll get used quite a lot as we go forward. Okay, so using those terms, we're now going to look at how we can use Taylor series to look at how error will propagate from a measurement to a prediction. So first off, we're going to use a change of variables where this is our measured variable. Right, and then f is the prediction. F of x tilde then would be the prediction made using that measured variable. And so this is just the Taylor series, but using a variable substitution where we set a equal to x tilde, our measured variable. And then we're going to use a first order approximation. And when we do that, we're not going to be using this term. And so taking the terms that we have left, we're going to just rearrange them. Right here. So this is the difference between the actual output if we knew x perfectly and the predicted output of this function based on the measured value of x. And so we can collapse this into just a single term that replicates what I just said. This represents a difference in difference from the measured prediction minus the true prediction. And we're going to say that this is approximately equal to f prime of x tilde. So this is the first derivative of f evaluated at our measured location, and this is the absolute value, multiplied by the difference in x. So this is what this is representing is a difference in our measured from the actual true value right here. So this right here is the error in x. And so what we're predicting here is the error in f of x. Okay, so we'll be using this equation now in order to compute how error propagates in various different cases. So to give you an example of this, we're going to do a biomedical example now. In echocardiography, they're trying to image the heart, and often they don't have a full 3-dimensional reconstruction of the heart. Instead, they have a 2-dimensional slice. And based on the dimensions in 1 dimension, they're trying to estimate a volume in 3 dimensions. And so they might use a formula like this, like volume equals some constant times that dimension cubed. And so what we're going to do is, because there's a lot of error in estimating these dimensions, we're going to look at how error in the measured dimension of negative plus or minus 0.5 would affect the expected volume from a calculation like that. So we'll first write down the measured diameter, or really dimension, you should call it, is 3.5. And we said that the error in that is 0.5. Okay, and then so then given our equation for volume right here, we'd say that the volume is 3.5 cubed times that constant. So this is just like simply using this value of 3.5, which equals 42.875 C. So this is just our central estimate, which is not really using the air propagation yet. The actual air propagation looks at when we're trying to calculate the error in V. And so we're going to be using this equation up at the top, where we need to be looking at the first derivative of our function with respect to x. So that would be a 3 times c times 3.5 squared, because it was cubed, and so its first derivative is going to be 3 times this, as such. And then we multiply this by the error in the measurements. The error was 0.5, so we're going to multiply this by 0.5. And you should get something about 18.375 C. So we see that there's substantial error in the predicted volume. And so I might write this then as that V equals 42.875 C plus or minus 18.375 C. So we see that, just around like a 15% error in the diameter leads to almost 50% error in the outputs. That's really substantial. Okay, so that's an example with one dimensions. We can also generalize that to multiple dimensions. And so the multi-dimensional Taylor series would look like this. So you'd have a function that has multiple x's, and so it had a zero-order term, and then instead of just one first-order term, it'd have many first-order terms. You'd have one first-order term for each variable, independent variable that you have, and so you'd have this one is just taking the partial with respect to x1, and then the next term would be taking the partial with respect to x2, and so on. And so using the same logic, if we rearrange this, we could come up with a multi-dimensional version of the error propagation, where we say that the error in the prediction of f right here is given by the partial derivative of f with respect to x1 times the error in x1 plus the partial derivative of f with respect to x2 times the error in x2, and so on, using this formula. So let's show you how you can use this in an example. So on the last one, we looked at predicting the volume, and so in this equation, we're looking at a different prediction about the heart, is computing its ejection fraction. And so what we're doing here is we're going to be comparing the volumes at diastole, which is when the heart is fully relaxed and is kind of stretched out, versus the volume of the heart when it's contracted down, which is called systole. So it kind of, as you see in the video, is going back and forth between diastole and systole. And the ejection fraction, or the amount of contraction overall, is estimated using this equation, which is 1 minus the dimension in systole cubed divided by the dimension in diastole cubed. And so this is just a way to estimate the volumetric contraction when only looking in 2 dimensions. And so what we'll do here is apply this basic idea that we did last time, but now on this multi-dimensional version that you see above. And so we'll start off by our central estimate given by this equation right here, that EF is expected to be 1 minus 2.4 cubed divided by 3.5 cubed, which is just 0.678. So that's our essential estimate of the ejection fraction. And note here that now we're going to be looking at the errors. So this is our delta this is our error in the diastolic dimension, and 0.42 is our error in the measured systolic dysfunction or function. And so the next thing that we need to do in the equation above, you see, is we need to take the first derivative with respect to each of the variables. And so I'll do that over here on the left. We say the rate of change in the ejection fraction with respect to d-cis is going to be given by, so we're taking this original equation and taking the partial derivative with respect to d-cis, and so you'll get negative 3 d-cis squared, and then nothing happens to the other term. Or in the other term, we need to take this with respect to the diastolic function right here. And so if you take the derivative of this function right here with respect to diastolic dimension, then you'll get 3 d-cis. So the d-cis is not changed, but you get a 3 out front, and you get d dia to the 4th power. Okay, so that's the little bit of calculus that we needed to do. And so now we can assemble them together and say that the actually, let me make a little bit more space here. Okay, so our error in ejection fraction is expected to be 3 times we have like these values where in d-cis we're going to plug in 2.4, and in d dia we would be plugging in 3.5, and then we multiply by 0.4 because that's the error in d-cis. And for our second term, we have 3 d-cis cubed divided by d dia 4 times 0.5, like this. And so if you multiply those through, you should get 0.161 plus 0.138 equals 0.299. And so so overall, we expect that the ejection fraction is around 0.0678 plus or minus 0.299. So that's showing that there's a very substantial, about 50% error in computing ejection fraction when you only have about like 15-20% error in the individual dimensions. And so hopefully that's a lesson in how much error can propagate through equations. So using these concepts, in your problem set number 3, you're going to be applying error propagation to some different problems, and it's going to be related to these tissue-engineered blood vessels. And in these tissue-engineered blood vessels, it's common to use a Poiseuille flow approximation that relates the pressure in the tube to the amount of fluid flow going through them. That's the term Q, and the radius of that dimension. And one of the critical elements is that if in a tissue-engineered vessel, if your pressure gets too high, you can get a rupture of your blood vessel. And if the pressure is too low, then you don't have enough to sustain blood flow. So that's going to be a very sort of clinically relevant problem for you to work with on your problem set. And in terms of application of this to the coding, you're going to be working with this series approximation for pi. And so you're going to make various pi calculators that utilize the different definitions of approximate and true error that we're going to have. So you're going to be able to compute how much error you have when you do a certain amount of iterations of this pi estimator function. So to summarize what we talked about today, we looked at how Taylor series can be used to approximate functions, that biomedical measurements are very prone to substantial error, and that using Taylor series, we can use these error propagation equations to examine how errors in input variables propagate to the outputs or the predicted values of these functions, either in single or multiple variable functions. So I hope that is useful for you, and I'll see you next time.